You know that feeling when you follow instructions to the letter, but the result just isn't what you expected? Well, it turns out that happens in chemistry all the time. Today, we're going to dig into why by exploring the world of reaction yields. Picture this, you're making cookies. The recipe says it'll make 3 dozen, easy. But when they're all baked and cooled, you count them up and you only have 32. What gives? Where did the other 4 cookies go? Believe it or not, that exact same mystery plays out in chemistry labs every single day. And we're about to find out why. So to really get a handle on this, let's forget about the lab for a minute and start somewhere a lot more familiar, the kitchen. We're going to use the world's simplest recipe, a grilled cheese sandwich. Now notice the perfect ratio here, 2 slices of bread for every 1 slice of cheese. It's a fixed recipe and that's crucial. In the world of chemistry, this is a lot like what they call a stoichiometric amount. It's the ideal, perfectly balanced recipe. But as we all know, life is rarely that perfectly balanced. This is where things get real, right? Because you don't have some magical, infinite supply of bread and cheese. You've just got what's in the fridge. So what happens when your ingredient count doesn't line up with that perfect 2-to-1 ratio? All right, let's move away from our perfect on-paper recipe and into a real-world kitchen. Let's open the fridge, check our inventory, and see what we're actually working with here. Okay, so here's the deal. We've got 28 slices of bread, but only 11 slices of cheese. Now, remember that recipe, 2 slices of bread, 1 slice of cheese. Let's just, think this through for a second. So before I show you the answer, try to figure it out yourself. You have plenty of bread, but maybe not so much cheese. Which one of these ingredients is going to be the bottleneck? Which one is going to decide how many sandwiches you actually end up with? The answer is 11. That's it. You can only make 11 sandwiches. And why is that? It's simple, because you only have 11 slices of cheese. Even though you technically have enough bread to make 14 sandwiches, the cheese runs out and the whole production line just stops. So this is the key idea. The cheese is our limiting ingredient. It's the thing that ran out first, and it limited the total number of sandwiches we could make. The bread, on the other hand, is the excess ingredient. We've got 6 extra slices just sitting there with no cheese to call their own. Okay, so that makes sense for grilled cheese sandwiches. But how in the world does this apply to actual chemistry? Well, let's take our kitchen analogy and see how it translates, almost perfectly, to a science lab. It's really the exact same principle. We just use different words. That ingredient that runs out first, in a chemical reaction, we call that the limiting reactant. And the one you have left over, that's the excess reactant. It's really that simple. And here's the formal definition, just so we have it. The limiting reactant is just whatever gets completely used up first. It's the thing that slams the brakes on the reaction and decides the absolute maximum amount of product you can possibly make. Okay, so we know reactions have limits, but how do chemists actually measure how successful or, how efficient a reaction was? How do you grade a chemical process? Well, first, there's something called theoretical yield. You can think of this as the perfect on-paper calculation. If every single atom did exactly what it was supposed to do, with 0 losses, this is the amount of stuff you'd get. It's the recipe promising you those 36 cookies. But then, there's reality. The actual yield is what you physically end up with at the end of the experiment. The stuff you can actually weigh. It's the 32 cookies you really got. And for all kinds of reasons, maybe the reaction didn't finish or some stuff got spilled, the actual yield is usually less than the theoretical one. So to see how close they got to that perfect score, chemists use this really simple formula. You take what you actually got, divided by what you theoretically could have gotten, and then multiply by 100. This gives you the percent yield. It's basically the final report card for your reaction. So let's look at a real example. A chemist does the math and calculates that they should be able to make a little over ½ a gram of pure copper. But when they do the reaction and weigh their final product, they only ended up with 0.392 grams. So what's the percent yield here? Well, you plug in the numbers and you get 77.3%. Not bad, a solid C+. But it's definitely not perfect. And that single number tells us a whole lot about how efficient that process was. So why do we care so much about getting a high percent yield? Is this all just about getting a good grade in chem class? No, not at all. This concept actually has some massive real-world implications. In fact, it's at the very heart of a whole field called green chemistry. The entire goal here is to design chemical processes to be as efficient as possible. That means creating more of what you actually want, the product, and a whole lot less of what you don't want, which is waste. And I've got the perfect example of this in action. And it's something many of us probably have at home right now: ibuprofen. The story of how we make ibuprofen has been completely transformed, all thanks to these principles of green chemistry. This is just incredible. The original way we made ibuprofen was only about 40% efficient. Just think about that. That means that for every bit of ibuprofen created, even more material was just thrown away as chemical waste. But then, a new, greener process was developed that's about 80% efficient, basically doubling the output and slashing the waste. And the impact of this new method is just huge. It nearly doubled the efficiency, which means it generates far less chemical waste, and it even uses safer materials to begin with. This was so revolutionary that it won a major environmental award back in 1997. It's cheaper, it's safer, and it's so much better for the planet. And this really is the whole point. Maximizing reaction yield isn't just some boring exercise in a textbook. It's about fundamentally rethinking how we make everything, from life-saving drugs to everyday materials. It shows that by understanding the limits of our ingredients, we can design a smarter, cleaner, more efficient world. The only question is, what will we improve next?